Hey, Chem30, welcome to topic number 7 called buffer solutions. This is a totally optional topic and will not be part of any assessment that you'll see at this level. It is something that you will see in post-secondary, and it's a challenging topic. So if you get a little bit of exposure to it right now, chances are you'll find it a lot easier in the future. So buffer solutions are solutions that contain both a weak acid and its conjugate pair. So we can think about a weak acid forming an equilibrium between it and the product, the conjugate, but the conjugate drives that equilibrium back. So we've got this solution where it can respond to the addition of H plus and OH minus. Okay, so these play an important role in many biological functions, including even our blood pH levels. Okay, so as we breathe in, we take carbon dioxide, which dissolves in the blood, which makes carbonic acid. And then as we exhale, it changes it to O2. So those processes are complementary, and they have to be in sync, or else we get issues happening in the bloodstream. So a buffer resists change because it's an equilibrium that involves the acid and a base. So the acid neutralizes added OH minus ions, while a base neutralizes the H plus ions. They have to be the conjugates of a weak acid-base pair. So CH3COOH, acetic acid, and its conjugate ion, CH3COO minus, or NH4 and NH3. There's lots of different common examples, but these are the most common that we'll see. So consider weak acid HX and its salt MX, where M is any cation that does not react with water. So we want an ion that doesn't play a role in it. So the HX is going to be something like CH3COOH, this guy here. And where we see MX is going to be sodium CH3CO minus, because when this dissolves in water, the sodium doesn't play a role and it just produces this. And this is that ion that can drive this backwards. So this will cause H plus to be created. When we add that ion, it consumes the H plus and drives this backward. Okay, so we get this back and forth motion, and we can see the Ka is equal to the concentration of H plus X minus over HX. Sometimes you'll see this as HA, but in this case, because we're working with an ion that can affect the pH, we generally write that as X minus. So when we rearrange the question, we can see that the concentration of H plus is equal to the Ka multiplied by HX over X minus, right? So it's just simple algebra to move that around. When we have hydroxide ions added to our HX, what we get is water being produced and that ion, or that anion, that can drive that reaction backwards. So if hydroxide ions are added to a buffered solution, they react with the buffer acid component to produce water and X minus. This reaction causes the concentration of HX to decrease and the concentration of X minus to increase. As long as the amount of HX and X minus are large relative to the amount of hydroxide added, then the pH doesn't change by very much. So instead of thinking about this as a neutralization equation, where as soon as we add an acid or a base and it lowers the amount of H plus and OH minus, we can sort of think this is being like a situation where an allowance is given. So let's say that a strong acid fully ionizes. So a strong acid has $100,000, it puts $100,000 on the table. And as soon as you start taking money away, the total amount of money from that table is decreasing. So if you're to take the pH of that solution, or an account of how much money is there, as that money gets used up or neutralized, it's gone. So it goes from 100,000 to 50,000 to 25,000 and so on and so forth. In a case of a buffered solution, there's a whole bunch of money on the table from the weak acid. It still produces some H plus ions, but when a base cancels that out, the acid again undergoes more ionization. So instead of having $100,000 on the table, it has $100,000 in the bank and only puts $5,000 on the table. So then you neutralize $5,000, it puts another $5,000. So it started at 100,000, put 5,000 there, so it's at 95. That 5,000 got used up, so it's at 90. Another 5,000 gets used up, so there's now only $85,000 in the bank, but there's always a consistent amount of money on the table. It never gets all used up at once. And that's the difference between a pH or a buffer solution and a strong acid or a strong base neutralization. As soon as those ions are neutralized, it's gone. The pH changes. But in a buffer solution, more ions are created to stabilize, to keep that pH at that same level. If H plus ions are added, they combine with the X minus to make the neutral molecule. Okay, so when we're talking about acidic solutions, they're only acidic because the H plus is being made. So if we take that H plus out and combine and turn it back into the molecule, the pH will decrease. Okay, and we see the same thing here. This is just the hydronium version of it, H3O plus. Okay, using either equation, we can see that the reaction causes X minus decrease and HX to increase. Again, if the change is small, the pH will be small, or the change in pH will also be very small. And this is what it looks like. So we can say that there is a buffered solution between these two things, right? HF is a weak acid, so HF will ionize to form H plus and F minus. The reverse of that is HF minus and H plus produce HF. So this is acidic, right? So we get that. And then when we have this being consumed and turned into this molecule, it's lowering the acidity, right? So if we add H plus, and we can see it down here, if we add H plus, then the concentration of HF increases because it drives that reaction back this way. And if we add OH minus, it drives the reaction this way. So we get the increase in concentration of this. And we'll see this a little bit more clearly after using this equation, okay? So we can see that there's a little bit of math happening here to calculate the pH of a buffer. So this is reliant on logarithmic laws, which you might have encountered in some of your math classes. But what we can do here is we can rearrange this equation to solve for the pH of a system that includes a base and an acid in it. So the pH of a system is equal to the pKa plus log of the base over the acid. Now, this is, if you want to kind of look at this and try and figure out what's happening, you're more than welcome to. Remember that log H plus is really just the pH. When we take the log of a Ka, we actually get a pKa. In the same way that pH, negative log H, is the same as negative log of Ka is pKa. Okay, so then you'll see that the negative log Hx over X gets rewritten as log of X minus over Hx. So it just gets reversed so that this symbol here is a positive. Okay, that's just a logarithmic law. Okay. But ultimately, this is what we're looking for here. So the pH is equal to the pKa plus log of base over acid. Sometimes you'll see written as A minus, so that acid, conjugate acid, or the conjugate base part. So an acid, a weak acid transforms into a conjugate base over the original acid. Okay, so in doing equilibrium concentrations, we can see that normally we can neglect the amount of acid or base that ionizes. So essentially where we made that approximation of some number minus X is equal to that same number, we're going to be able to still do that because the concentrations of the acid and the base are sufficiently high that when the concentration changes because of the addition of OH minus or H plus, it's negligible. Okay, so I'm just going to say that again. When we add an acid or a base to a buffer solution, the concentration of the weak acid or the weak base ion is high enough that it essentially makes no difference. The concentrations are strong enough. Okay, so the weak acid, weak base changes, again, are something like a billionaire losing a couple of dollars. We're not going to be able to notice it. So we're going to make that approximation. Okay, we got our first example here. What is the pH of a buffer that is 0.12 molar lactic acid and 0.1 molar sodium lactate? For lactic acid, the Ka value is 1.4 times 10 to the negative 4. So this might seem a little overwhelming based on what you know about buffer solutions, but you just got to take it one step at a time. So let's write out what this equation would be. So CH3COOH aqueous, there's our lactic acid plus water, reacts to form CH3COO minus aqueous and H3O plus aqueous. Okay, so we have to recognize that we've got two substances here. We've got some lactic acid, which is pretty straightforward, and then we got some sodium lactate. So sodium lactate is just the ion. It's that HX version of this, or in this case, MX. So in this case, the metal is sodium and X is CH3COO minus. Because we know that anything connected to sodium is soluble in water, then the concentration of that is equal to the concentration of that acetate ion. So the concentration of that must be 0.10 molar. So in order to sort of show our information, we're going to write out an ice table here where we got initial, change, and equilibrium. We've got initially 0.12 molar of that. Water is a liquid, so we don't ever write it. And then we've got the acetate ion is equal to 0.10 molar. And then we've got no H3O plus. We assume that there's none in solution. So this is going to be 0 here. And then this would be minus X, 0.12 minus X. This would be 0.10. And, because we know that there's no hydronium or H3O plus, we would assume that the product side is going to be increasing. So this is going to be plus X, 0.10 plus X, and then this is going to be plus X and X here as well. We can just assume that the concentration change in both the acetic acid and the acetate ion, symbolized by X, is insignificant. So in the end, then we get 0.12 is equal to the concentration of the acetic acid. I'm just going to write this in red. So 0.12, and same thing with the acetate ion, 0.10. And then we don't know the concentration of the H plus. Okay, but it's asking us for the pH of this. We could solve that X value using the Ka, but we can sort of use the equation that was listed on the previous slide or 2 slides ago, the Henderson-Hasselbalch equation. So this Henderson-Hasselbalch equation is pH is equal to pKa plus log of base over acid. And I always write it like that because it's a little bit more clear than X minus and HX. So we've got base over acid. So our pH is going to be equal to negative log of our Ka plus log of our base, which is 0.10 over our acid, 0.12. So we get this negative log of 1.8 times 10 to the negative 5 plus log of 0.1 over 0.12. And you can just punch this into your calculator, and it actually works out to being 3.77. Okay, there shouldn't be any surprises there. It's a pretty straightforward calculation. Okay, so we just need to be able to pull that information, write ourselves an equation, and put it into the Henderson-Hasselbalch equation. You'll see that as written as HH equation sometimes, and we get our answer. Okay, there's a second example for you here for benzoic acid and sodium benzoate. So benzoic acid is our HX, and then our sodium benzoate is the MX. And again, the sodium isn't going to play a role. Okay, so I'm going to stop the video and just work this one out. Pause it if you like and try it on your own. Alrighty, we've got another challenging one here. It's asking us, how would we make a buffer solution? So how many grams of ammonium chloride must be added to 2 liters of 0.1 molar ammonia to form a buffer whose pH is 9.0? So assume that the addition of the ammonium chloride does not change the volume of the solution. So this is challenging because instead of working with an acid that we're creating a buffer solution with, we're actually starting with a base. So we have to alter our Henderson-Hasselbalch equation. So let's write out an acid ionization equation and then see how that would work if we started with the base instead. So we know that HX plus H2O is at equilibrium with, I wrote HA, there we go, HX is at equilibrium with X minus and H3O plus. So when we write the Henderson-Hasselbalch, it is pH is equal to the negative log of Ka plus log of base over acid. So we can see that this value here represents the base, and this value here is the acid. And by taking and putting those things into our equation, we can account for this. So the amount of H3O plus, this guy here, is dependent on the Ka, and that's why we have that part right here, right? The higher the Ka, more H plus is made. So if we take and imagine this to be a base instead, so the general form of this is base plus H2O forms, right? So bases accept hydrogen, so we get Hb plus and OH minus. Okay, so here's our base and here's the acid. So we're going to get a reverse sort of thing happening with the log expression. And instead of having a Ka, we're going to work with a Kb. And because we're ultimately figuring out the concentration of the OH minus ion and taking the negative log of that, instead of having a pH, we're going to have a POH. So we get POH is equal to PKB, so the negative log of Kb, plus log of acid over base. Okay, so let's take this information that we're given here and solve this. So we should recognize that POH is equal to 14 subtract the pH. So that gives us 5.00. So we can write out our equation now. So POH is equal to PKB plus log of acid over base. So we're going to get 5.00 is equal to negative log 1.8 times 10 to the negative 5, which is the Kb value for ammonium, plus log of acid, which is unknown. So we're going to write that as X over the base, which is 0.10 molar. So we're going to get 5.00 is equal to 4.76 plus log X over 0.1. When we move that 4.76 over, we get 0.24 is equal to log X over 0.1. Now, according to logs, okay, so log A over B is equal to log A subtract log B. So we're going to rearrange this part of it. So we're going to get 0.24 is equal to log X subtract log of 0.1. Log of 0.1 is negative 1. With that negative, it changes to positive 1. So we get 0.24 is equal to log X plus 1. So subtract 1 from both sides. And we get 0.76 is equal to, negative 0.76 is equal to log X. Well, then log, the opposite of log is to the power of 10, right? So we're going to use that anti-log button, or take 10 to the power of 0.10 to the power of negative 0.76 is equal to X, and that works out to being 0.18. Now this represents the concentration of NH4. So we need to go through a couple of steps. So the concentration of NH4Cl has to be 0.18 molarity, but this is asking us for how many grams. So we're going to multiply it. We should recognize that molarity is in moles per liter. So we're going to multiply by the 2 liters that we have here in the solution and then the molar mass of this. So 1 mole of NH4, and sorry, I'm running out of room, is 14.01 plus 4.04. That's the 4 hydrogen, and chlorine is 35.45. Gives me a molar mass of 53.5. So when we multiply 53.5 grams, when we multiply these, our liters disappear. So liters from here and here, moles disappear from here and here. And we have a solution of, you betcha, 19. It's actually, I think, 19.23 grams, 0.18 times 2 times 53.5 is 19.26 grams. So we round that down because our sig figs here only has 2 numbers. So our answer should only have 2 as well. So 19 grams. So if you take 19 grams of ammonium chloride and sprinkle it into 2 liters of 0.1 molar ammonium, you'll get a solution with a pH of 9. So the buffer capacity and the pH range are two important qualities of buffer solutions. The capacity is how easily able it is to resist a pH change. Okay, so a solution of 1 molar acetic acid and the ion of that, acetate ion, 1 molar as well, has a greater capacity to buffer solution than 0.1 of both of those species. Why? Because there's more ions that are able to neutralize added acid or added base. Okay, so there's more available to work with. The pH range is the range over which that buffer solution can effectively neutralize or resist a pH change. Okay, and it is most effective when it's within 1 pH unit of the pKa. So if you take the Ka or Kb value, the negative log of that, and you determine that value, it's effective within 1 unit of that. Okay. It's important to understand that the reaction between a strong acid and a weak base essentially goes to completion, as does a weak acid and a strong base. This means that if we do not exceed the capacity of the buffer, then we can assume the added species is entirely consumed by the buffer. What this means is when we add in a strong acid or a strong base, the strong acid or strong base puts all of its money on the table and gets used up by the buffer, as long as you don't exceed the number of ions available. Okay, so think of it like this. A buffer solution has $100,000 in a bank account and only puts $5,000 on the table. A weak acid comes in and takes that $5,000, and it keeps on taking until it's all used up. So $100,000 in the bank, $5,000 on the table. The strong acid or the strong base comes in and puts all $80,000 onto the table. It only gets used up $5,000 at a time as the buffer solution keeps on adding or neutralizing that. But as long as the bank account of the buffer doesn't run out, it's going to neutralize that solution. So all the cash of the strong acid or the strong base gets used up, and there's some cash available still in the bank of the buffer solution. To calculate the pH change after the addition of a strong acid or a strong base, we're going to use these steps. We're going to figure out how many moles of buffer there is. We're going to figure out how many moles of acid, strong acid or strong base have been added, subtract those, figure out the new concentrations, use the Ka, Hx, and X minus using the Henderson-Hasselbalch equation to determine the new pH. So we've got this example here. A buffer is made by adding 3 moles or 0.3 moles of acetic acid and 0.3 moles of the ion version of this to enough water to make 1 liter of solution. The pH of the buffer is 4.74. We are going to first calculate the solution of this solution, the new pH of the solution after 5 mils of 4 molar sodium hydroxide is added. And then we're going to see how much the pH would change if we added that same amount of hydroxide to pure water. See if a buffer solution, how much a buffer solution can control the pH. Okay, so our reaction here is going to be CH3COOH aqueous plus H2O liquid ionized to form CH3COO minus aqueous and H3O plus. Okay, so initial change in equilibrium. Initially, we've got 3 moles of this in 1 liter, so that's going to give us 0.300. Waters we don't have a concentration of, and we also have concentration of this acetate ion, which works out to being the same number, so 0.300. Okay, and originally we've got no H3O plus. It's being used up, so we've got nothing of this. So when we add the sodium hydroxide, NaOH, we really want to talk about this in moles because NaOH breaks down into Na plus and OH minus. This OH minus is going to remove this. So right, if we imagine CH3COOH plus OH minus, it's going to make CH3CO negative and H2O liquid. So this H2O isn't going to make any difference here, but it's going to decrease this and increase this by that same amount. So if this was 4 moles of this, it would lose, this would go down by 4 moles, and then this would go up by 4 moles. This gets used up, this gets used up, right? That's what we were talking about on that previous slide. All the strong acid or base gets used up, and it consumes some of that buffer solution. Okay, so what we want to do is we want to figure out how many moles of OH minus are being added. So we're going to take the concentration of NaOH let's write it like this. So number of moles of OH minus is equal to the concentration multiplied by the volume. So the concentration here is 4 molar, so quite strong, 4 moles per liter. And it tells us that 5 milliliters is 0.005. This works out to being 0.02 moles. So when we add that into our chart here, we know that this is going to go down by 0.2 moles, and this is going to go up by 0.2 moles, right? We know we saw that right up here. So this is all going to be consumed 0.2. We add this. So this goes down by 0.2, and then this is going to go up by 0.2. So this works out to being 0.280 moles, and this works out to being 0.320 moles. Now, normally we would account for a volume change here. We've got 1 liter of solution and then 5 milliliters. So our new volume would be 1.005. And we could take these two numbers and divide by that. But in the end, it's not going to change it enough for it to be significant. Okay, so we're just going to use these values and assume that the volume essentially is still 1 liter. Okay, so when we do that, we can figure out the pH, because that's equal to negative log of Ka plus log of base over acid. So we get negative log of 1.8 times 10 to the negative 5 plus log of our base is now 0.320 molarity. Our acid is 0.280 molarity, which works out to being, so negative log 1.8 times 10 to the negative 5, that's the Ka value for acetic acid, plus log of 0.320 divided by 0.280 equals to 4.80. So we can see that the addition of that sodium hydroxide changed the pH originally from 4.74 to 4.80. So a very small difference. So 0.06, pretty insignificant, because it's able to resist that. So it's like having $100,000 in the bank account. Sodium hydroxide comes in and plops its money on the table, or takes away some of that money of the acetic acid, but it replenishes it. So the pH stays relatively consistent. Now, let's look at how much the pH would change if we were to add that same amount of sodium hydroxide to water. So let's say that we've got we got sodium hydroxide, NaOH, aqueous, breaks down into Na plus and OH minus. We know that we get 0.02 moles, 0.02 moles of this in our 1 liter of water. So the concentration of the OH minus would be 0.02 divided by 1.000 liters, which works out to be 0.02 molarity. We know that this is a strong acid, therefore the concentration of strong base. Therefore, the concentration of the strong base is equal to the concentration of OH minus. So if we want to figure out the pH of this, we would go negative log of our OH minus, in this case, that's equal to negative log of 0.02. So negative log 0.02 works out to be 1.70. Okay, and that's our POH, right? Can we just took the log of our OH minus? So pH is equal to 14 minus POH. So subtract 14, and we get 12.30. So we can see that the addition of that same volume of sodium hydroxide would take a neutral solution, so 7, and change it to 12.30. So it changes it by more than 5 pH. That's huge, right? So we can see that a buffer solution really does resist a pH change because of that equilibrium reaction that's going on. Hopefully some of that made sense to you. If you have any questions or concerns, please reach out. Otherwise, have a great night, Chem 30.